In the previous video, we saw that as the marshallian demand responds to a change in price, it can be decomposed into the substitution effect and the income effect. Because the substitution effect is entirely captured by the expenditure minimization problem, it is equivalent to the change in the Hicksian demand. In this video, we will further discuss the relationship between these two types of derived demands. We did the hard labor previously and derived these demand functions algebraically. To strengthen the intuition, we'll now look at how the derivation works through graphically. For the marshallian demand, it is the result of the utility maximization problem. From the algebraic solutions we derived before, we know that the marshallian demand is a function of its own price, so we would be able to plot it on a graph. As of the derivation of marshallian demand graphically, we saw that in the previous video, the decrease in the price of a horizontal good will rotate the budget constraint outward around the vertical intercept. As the constraint rotates out, the tangent point moves along outward as well. And each step of the way, the effect is a combination of the substitution effect and the income effect. If we keep track of the price of the horizontal good, which is beer in this case, and its corresponding demand, then we can plot the following graph in panel B, whose horizontal axis is lined up with the graph above. In the graph above, we have this path of optimal consumption bundles as price of good 1 changes. This curve is called the price consumption curve, a very similar idea to the income consumption curve that we have seen before. Now let's look at the Hicksian demand. We know that Hicksian demand is derived from the expenditure minimization problem, which holds the utility level constant. In the graph above, let's imagine that we start from the optimal consumption bundle of E2 here, where the per dollar utility of good 1 and good 2 are equalized. If the horizontal good now becomes more expensive, then the price ratio becomes higher. Then the expenditure curves become steeper. So an expenditure minimizing consumption bundle will shift upward along the scene difference curve to somewhere like E1. This is precisely the substitution effect without any income effect. The intuition is that after the increase in price, per dollar utility of good 1 becomes lower. So even if the consumer can be flexible in the budget, they will substitute some good 1 with good 2 to reach this utility level in order to save expenditure. Similarly, starting from this point of E2, if the horizontal good now becomes less expensive, then the price ratio becomes lower, and the expenditure curve becomes flatter, and the expenditure minimizing consumption bundle will shift downwards along the indifference curve to somewhere like E3. The intuition is that after the decrease in price, per dollar utility of good 1 becomes higher, so the consumer will substitute some good 2 with good 1 to reach this level of utility in order to save expenditure. If instead of a decrease in the price of good 1, if the price of good 2 has increased, we'll see exactly the same effect. That moves down the indifference curve from E2 to a different consumption bundle that sits lower on the indifference curve. Now, if we keep track of the price level as it changes and the resulting demand holding the utility level constant, then we can also plot a demand curve. And this is our Hicksian demand curve, as illustrated below by this darker blue curve here, that is denoted by H. We can see that at different price points, the demands here at E1, E2, and E3 along the Hicksian demand curve corresponds to these demands for good 1 from the graph above. The key idea here is that Hicksian demand reflects the substitution effect and the substitution effect alone. So how does the marshallian demand curve, marked by D here, relate to the Hicksian demand, denoted by H? Well, the key lies entirely on the income effect. Let's look at the response in demand as price increases. On the left-hand side, we have a graph that we've seen in the previous video, where the price of the horizontal good had increased. So the budget constraint rotates in from the vertical intercept, and the optimal consumption bundle changed from E1 down to E2. And remember, this is actually a change in the Marshallian demand. If we think about the change in Hicksian demand, it is only moving from E1 down to this level marked by E star. If we think through the utility maximization problem again, you can think of any arbitrary price for a good, let's say 50 cents for the good on the horizontal axis. And then, given the budget and the price for the other good, you can find the optimal consumption bundle under a proper utility function. From there, you can find the utility level at the optimum, let's say here. We learned that if you pick this utility level, let's say the utility level at I1, and then minimize expenditure given the same prices, you will have exactly the same consumption bundle back, which lands back exactly at E1. So the Marshallian demand and the Hicksian demand are equal to each other at this point. Now, if we look at the graph on our slide, this is exactly why we can always find a Hicksian demand that crosses the Marshallian demand at an arbitrary point. All we need to do is to pick the price level that leads to the Marshallian demand at this point, and then solve the dual problem with the utility level that the Marshallian demand gives you. The resulting Marshallian demand and the Hicksian demand will overlap. Now consider this price of 50 cents at a starting point, and we start to raise it. Then the optimal response from the expenditure minimization problem and the utility maximization problem will start to diverge. And this is exactly what is shown on this graph on the left-hand side. If we look at the model in these nodes, the expenditure minimization problem will try to find the demand that reaches the original level of utility while minimizing cost. And this is a Hicksian demand that only captures the substitution effect. In other words, the Hicksian demand for good 1 was at the horizontal coordinate of E1 and now reduces to the horizontal coordinate at E star. On the demand curve here, we see that as the price increases, the Hicksian demand falls back, and that's exactly why the demand moves down from the level at E2 to level at E1 as the price increases from 50 cents to $1. But why is the Marshallian demand here flatter than the Hicksian demand? Well, the utility maximization problem doesn't try to guarantee the same level of utility that the consumer was able to reach before. Instead, it is restricted by the same budget. So the utility level must decrease. And the optimal solution here, which is Marshallian demand, reduces from the level of E1 all the way down to here at the level of E2. Now, using the decomposition we learned from the previous video, the change in the Marshallian demand is the income effect combined with the substitution effect that is captured by the Hicksian demand. In other words, the income effect pushes the Marshallian demand further back from the Hicksian demand level at E star. So if the good is a normal good, then the income effect pushes the demand further down, just like what is illustrated here on this graph. If the demand is an inferior good, however, then the income effect would actually increase the demand and offsets some of those decreases from the substitution effect. If we look at the graph on the slide here, we notice that the Marshallian demand rotates further back comparing to the Hicksian demand on this graph. For normal good, the income effect decreases the Marshallian demand further on top of the decrease in Hicksian demand. The response when price decreases is very similar, just in the opposite direction. As price decreases, the substitution effect has the consumer switch towards this good. So the Hicksian demand increases from the level of E2 to the level of E3. For normal good, the income effect would further push out the demand, driving the marshallian demand even higher from the Hicksian demand, because the consumer is now effectively richer. In other words, for normal goods, the Hicksian demand is steeper than the marshallian demand, because the response in marshallian demand is exacerbated by the income effect. So the marshallian demand is more elastic than Hicksian demand. Can you think about how the two demand curves would compare to each other if the good is an inferior good? Which demand will be steeper? Now, in addition to being a very good reference point in thought experiments, the Hicksian demand is actually a very useful tool in policy analysis. We'll discuss more about this point later in the class, and we'll see more examples of it in more advanced classes. The relationship between the marshallian demand and the Hicksian demand can be summarized by a very compact expression. This expression is called the Slutsky equation, and it describes our previous intuition in a very precise manner. The expression says that as the price increases, the response in the marshallian demand, which is measured by the price elasticity of the marshallian demand, epsilon, can be related to the response in the Hicksian demand, which is measured by the price elasticity of the Hicksian demand function, epsilon star. And the difference between them is measured by the product of theta times xi, where theta is the expenditure share of the good in the budget, and xi is the income elasticity of demand. This product seems familiar to us because we have seen it appear in our previous video where we talked about theta 1 times psi 1 plus theta 2 times psi 2 is equal to 1 equation, when we talked about the effect of income on demand. Broadly speaking, the expression captures our previous intuition that the total effect, which is captured by the marshallian demand, is a substitution effect which is captured by the price elasticity of demand of the Hicksian demand, plus some term related to the response of the demand to changes in budget, which is the income effect. The income effect depends on two different terms: how sensitive the demand is to changes in the budget as measured by the income elasticity of demand, but also it depends on how much expenditure the good take up in the budget of the consumer, which is theta. It is quite intuitive why xi, the income elasticity of demand, would affect the income effect. But why does theta matter? Now let's compare two different scenarios to understand this point. Think about the price of coffee increased by 10%, or the monthly rent of your apartment increased by 10%. Which case would put more pressure on your budget? Well, definitely the rent. If I spend half my summer intern salary on rent and a very small fraction of income on coffee, then a 10% increase in the rent cost will have a huge impact on the purchasing power of my income or budget. But because the coffee takes such a small share of my budget, a 10% increase in its price doesn't really have nearly as big an effect. So if a good has a bigger theta, then each percentage increase in its price will have a bigger impact on the effective income. On the other hand, if the demand of a good is more sensitive to changes in income, as measured by xi here, or xi is bigger, then the income effect will also be more significant. So the overall income effect is a combination of these two terms, or two different parts of this channel. Theta controls how much the change in price affects the effective income, and then xi controls how much the effective income affects the demand of this good. So why is there a negative sign in front of the income effect? Our intuition says the total effect is a combination of substitution effect and the income effect. So shouldn't the sign be positive instead of negative? The reason lies in the detailed reasoning. For normal good, the product is positive because the income elasticity of demand is going to be positive and the consumption share must be positive as well. The interpretation of the positive income elasticity is that the demand will increase by xi% when the income increases by 1%. But when the price increases, the effective income doesn't increase. It actually decreases. So when we evaluate the effect of the price increase on demand by taking the derivative on these quantities, we need to look at the effect of a decrease in income instead of an increase, which is why there is a negative sign here, which effectively flips that effect for us. If you're unconvinced about this argument, don't worry, we'll derive the equation in just a little bit, and you will see that the negative sign falls out very naturally from the derivation. To get familiar with the Slutsky equation, let's first do a practice problem to warm up to the notations. The Slutsky equation has 4 notations. 2 different price elasticities, epsilon and epsilon star, and the consumption share of theta and the income elasticity of xi. So if we have any 3 of these variables, we can back out the 4th. Let's say that we have a consumer, Jackie, who spends 40% of income on music subscriptions, and her price elasticity of demand is epsilon equal to -1, and her income elasticity of demand is xi equal to 1. Then, using the Slutsky equation, we have that epsilon is equal to the substitution effect, epsilon star, combined with the income effect, which is negative of theta times xi. So now we have epsilon from the question, we have theta, and we have xi. Plugging in these values and rearrange, we can find that epsilon star is just minus 0.6. Not too bad, is it? All right. Now we're familiar with the notation and the idea of it, let's try to prove the Slutsky equation. The proof only has a few lines, but each line requires a very thorough understanding of the entire consumer's choice model. Just like our argument relating the marshallian demand to the Hicksian demand, we will start from arbitrary price. And at this price, we can find marshallian demand from the utility maximization problem, which, let's say, points us to this demand at E1. Now, using the optimal utility level that's represented by the U bar at the scene difference curve of I1, we can solve the expenditure minimization problem, which will then also give us exactly the same demand at E1. And the expenditure level that is incurred at the consumption bundle at E1 is then given by the expenditure function of E. To turn it another way around, if we solve a utility maximization problem with this particular expenditure level of E, then we'll also find exactly the same optimal demand and the same utility level as U bar. So all these 3 objects are equivalent. In other words, when we're at the optimal consumption bundle, the Hicksian demand is the same as marshallian demand, and which is the same if we just solve the utility maximization problem to take the budget level Y at the expenditure that is incurred at the Hicksian demands to reach the utility level of U bar. And that's exactly the same idea as what we're trying to represent here in this graph at the point of E1. And what we will try to do in this proof is that because we understood as the price changes slightly, once we start to move away from this point of E1, the expenditure minimization problem will lead to a different solution compared to the utility maximization problem. So the 2 solutions are going to diverge. But how they diverge away from this point is going to be somewhat related. And we're going to look at this relationship algebraically through a derivative. To do that, we're going to focus on a particular part of these equivalences. In particular, we're going to pick out the Hicksian demand and the marshallian demand when the budget is this expenditure level that is reached at the optimal consumption bundle. And we know that before the price change, these two quantities are exactly the same. They're just Q1 at that optimal bundle of E1 we just saw on our graph. Now from this point, we will try to increase the price slightly and let each component respond to that. As the price increases, the Hicksian demand changes on the left-hand side. Meanwhile, on the right-hand side, what we notice is that the price changes right-hand side through two different channels. There is a direct effect on the marshallian demand, holding the expenditure constant, which is saying that the consumer will now perhaps buy more or less, given that they will have exactly the same amount of expenditure as before. But there is also a second channel, which says that as the price increases for good 1, the expenditure that needed to reach the same utility level of U bar as before is gotta be different. And as expenditure change, the marshallian demand would also change as well. And that's our second term here. So the total change on the right-hand side is a combination of these two effects. The first effect is a response in quantity to the changes in price when the expenditure is held constant, which sounds really like total effect. And there's a second effect, which is the change in quantity demanded for good 1 coming from the change in the expenditure, given that the expenditure needed to reach the original utility level had to increase. So now we have these two effects combined on the right-hand side. To move on from here, we need to invoke the Shepherd's lemma, which says that the derivative of the expenditure function with respect to the price of a good recovers the Hicksian demand of that good. And at the starting point where the Hicksian demand and the marshallian demand overlap, the demand is just the optimal quantity, or Q1, at the point of E1 on the graph. Now we have a lot of derivatives, and the Shepherd's lemma has a lot of elasticities. So we will try to rewrite these derivatives into the form of elasticities. And notice that, again, because Hicksian demand and marshallian demand takes the same value at the starting point of E1 in the graph, they are both Q1. So we have essentially dQ1, dP1 here, and dQ1, dP1 here, which appears on both sides of the equation. So now let's try and multiply the ratio of P1 over Q1 on both sides of the equation, and then we might be able to write these things into the form of elasticity. Once we multiply this term P1 over Q1 on both sides of the equation, we found that the first two terms of the equation become elasticity of demand. The first term becomes the price elasticity of demand for the Hicksian demand, which is epsilon star. The second term becomes the price elasticity of demand for the marshallian demand function, which is epsilon. In addition, for the third term, we now have derivative of Q1 with respect to the expenditure. And expenditure is the same as budget or income. So to write it into the form of income elasticity of demand, we need the ratio of E over Q1. But we already have Q1 here on the bottom, so we just need to make up an E out of nowhere. So let's use our trick of multiplying 1 again, and to multiply this ratio of E over E. So now the right-hand side becomes epsilon, which is coming from this term, plus xi, which is coming from this derivative, times E over Q1. And that's our xi. And what's left over is Q1 times P1 over E. And again, that's just expenditure share of good 1. Finally, we just move this term of plus theta times xi to the other side of the equality, and then flip them backwards. And then we'll have epsilon on one side, and then epsilon star on the other side, minus theta times xi. And there we have it. This is our Slutsky equation. This proof is not long at all, but it requires a very deep understanding of all of the modeling parts in our consumer's choice model. Learning this proof is a great way to deepen our understanding of the connection between each part of the framework. We will now conclude with a diagram that summarizes our consumer's choice model. We have already seen most part of this diagram at the end of the previous section. We started out with axioms of consumers' preferences, which provides us with the properties of the indifference curves. From there, we built two different consumers' choice models that are closely related to each other. Their derived demands overlap at a particular instance, but their responses to changes in prices are different, because one ensures that the budget is held constant, whereas the other holds down the utility level the consumer is able to reach. So they're bound to diverge when the price changes. However, their differences in the response to a price change is connected by the income effect. And the Slutsky equation precisely summarizes this connection for us. Now we have a very complete view of our consumer's choice model. In the next section, we'll turn to look at the welfare implications coming from the demand models.